The guidance, navigation, and control work package has been working on the controller development, integration, and ensuring the crane performs well in all its missions. Our flight dynamics model developed in Simulink can be seen running with ArduPilot software in the loop simulations. The SITL ArduPilot controller calls the FDM backend and runs in a loop. MAVProxy is being used for the ground control station here for data visualization and capturing logs, which are then compared against test flights. The vehicle data and properties were taken from the mechanical design, aircraft design, and aerodynamics work packages. These include the vehicle inertias, center of mass, and aerodynamic properties of the crane. By connecting MATLAB and Simulink to ArduPilot SITL, we further determined the optimal tuning parameters for the flight control system. System identification method was used to find the dynamics of a system by collecting data, and refined our flight dynamics model. This was tested on a smaller drone by automatically introducing frequency sweeps into the roll, pitch, and yaw rate controllers. This allows us to estimate the transfer function for each of the axes. Here, we can see excitations in roll. The transfer functions are developed from flight logs, which are then fed back into the flight dynamics model. This was applied for the subscale crane model and will further be performed on the full-scale platform. Our refined gains from the FDM model are tested and validated in a software-in-the-loop environment using Gazebo as the physics engine. Gazebo offers realistic 3D simulation and seamless integration with subsystems like situational awareness through ROS2, which also visualizes real-time sensor data. In Gazebo, we use the lift-drag plugin to simulate aerodynamic behavior by modeling forces and moments from each lifting surface and propeller. By setting parameters such as lift and drag coefficients, angle of attack, air density, and reference areas, realistic aerodynamic responses are generated under varied flight conditions. These forces are applied directly to the vehicle model in real time, capturing its dynamics during maneuvers. A 360 LiDAR was installed on the crane to provide detect and avoid capability. The GNC team uses open-source hardware and software to visualize obstacles, while a path planning algorithm guides the aircraft through them. Crane will also use radar for obstacle avoidance, with the 360 LiDAR serving as validation. Our radio and communications team has been working with our partners BChat in developing and testing their Chaonic 1S modules running Reticulum on a Linux-based board. The team was able to successfully test the ground equipment before installing them on the crane. A Skywalker X8 fixed-wing UAV platform was used for the validation test flights, ensuring communications range. The module features video feed along with data link telemetry and C2 link, all in one comms device, ensuring a stable connection through the range tests. A sample video feed from the camera systems can be seen from 120 feet above ground level, about 2 miles away from the operator, fulfilling requirements for the crane. In search and rescue, you rarely get a second chance to land safely. Here you see CraneAero's situational awareness. From live or recorded video, it proposes and ranks landing zones, locks on the best candidate, and keeps the operator in control through a cockpit-style GUI, with everything logged for audit and handoff to the flight stack. At its core, the system fuses semantic landability with instance-level avoidance. From altitude and camera field of view, it computes a physically correct landing footprint, adapting for pitch, even estimating from sky ratio if gimbal data is missing. Candidates are ranked, stabilized with a hysteretic dynamic lock, and shown clearly in the GUI: white for candidate, blue for pending, red for confirmed, ellipse for semantic, triangle for instance guided. Setup is simple. Connect an RGB or EO camera, set field of view, and input altitude if telemetry is absent. The pipeline is resilient, with fallback loaders and super resolution keeping the app responsive. Operators control scope, whole frame, focus ROI, or allowed region, and strict class gates ensure nothing is drawn until confirmed. Each frame runs super resolution and 2 inference paths, instance masks and terrain semantics. Semantic maps are smoothed, refined to UAV footprint size, and hazards are carved out early. Candidate centers are spaced to avoid clutter, while a safe zone grid uses optical flow to reject motion near people or vehicles. Dynamic locking holds the best target unless a superior one emerges, preventing thrash in dust or gusts. For handoff, compact geometry, target center, axis, sky ratio, and ID is published, with synchronized logs for validation. Stage 3 integrates LiDAR or radar to add slope and clearance. Risk controls are built in: physics-grounded geometry, gating, hysteresis, and validation tests for timing, stability, and degradation. In short, autonomy with accountability, dual-path perception, stable and explainable lock, and a human-in-the-loop HUD engineered for safe SAR landings.